anything you want to talk about from homeworks 1 or 2, we can take a few minutes at the start here to get after that. Josh.
Okay, I did how to do the multiplying and dividing.
Okay.
I'm a little bit confused on like adding and subtracting.
Okay. Is there one you want to look at in particular? Sure. Okay. So number 8 here, I'm going to factor in the denominator so that I can find a least common denominator. Now x plus 1, there's nothing to do. X squared plus 1, I know, is a difference of 2 squares. And then 5x minus 5, I know I can take out a greatest common factor. So my least common denominator is going to have a 5 in it, an x plus 1, and an x minus 1. Since the most time that the x minus 1 occurs in any fraction is once, I just have one of those. And the same thing with the x plus 1. In any one fraction, the most times that occurs is one time. So I just need one of those. Is that okay? So I multiply all those pieces out and combine like terms. Is that okay? And I don't know why you guys said this was okay, because I wrote down the wrong thing here, right? That's not supposed to be. Does that feel better? Somebody should have been like, hey, Josh, you good?
Yeah.
Are you sure? Did I bulldoze through anything? Something we can, I can do?
I'm just still confused on like the least common.
Okay. So if I had denominators of like 3, 5, and 7, the least common denominator would just be like 3 times 5 times 7, right? That's basically what I have here. Or if it was like, let's make it a little bit trickier. Let's say we have 15, 35, and then like 7. Well, I have 3 times 5, I have 5 times 7, and then I just have 7. My least common denominator is still going to be like 3 times 5 times 7, right? You agree with that? So it's the same idea here, right? I have x plus 1, that's like, I have x plus 1 times x minus 1, that's like 5 times 7. And then I have 5 times x minus 1, that's like 3 times 5. Does that feel any better? Back to something we feel a little bit more comfortable. Yes, Mackenzie. Oh, we haven't finished yet. We'll get to it. Since we haven't crossed anything out, though, there aren't any restrictions generated yet. It's only if we have to do any crossing out that happens. Edmund? Yeah, we're not finished with this one, though, yet, right? Okay. So the key is just thinking about those, like those monic pieces, those linear polynomial parts, as like one thing, right? Like x plus 1 isn't 2 things. It's not x and 1. It's just like 1. Okay, so let's FOIL all this stuff out and multiply it together. I'm going to do that kind of all in one step. Is that okay? So I have 5x squared plus 50 minus 20 minus x squared minus 4x minus 3. So I distributed the negative on that last piece also, in addition to FOILing. That's why all the signs are negative there. And like if you did 100 of them, you might see it once or twice. I have to be pretty careful and like really kind of plan it out. I just can't write stuff down and expect to get a restriction generated from it. Josh.
You do one with restriction.
So that would be more appropriate for a multiplication and division problem, which I'm happy to do, but these adding and subtracting ones, I don't know that any of the adding and subtracting ones had a restriction on this homework set. Do you still want to do one? Okay, I'm happy to do that. And I know that we've wanted to do some other problems too, and we'll circle back to those guys. We're not going anywhere. This question has kind of come up. Let's kind of get after this before we move on to number. Any of them is fine. I'm going to do 1 just for the sake of argument. Not a big deal. Restriction. So it's just setting whatever that piece that you've crossed out completely equal to 0 and solving. Right? So this one gives us a -7 because when x plus 7 equal to 0 and I solve, I get negative. Is that okay?
Yeah.
Okay. Eddie, you wanted to do 9. Okay. So again, I'm going to start by factoring. And the denominators are the only places that... So that's a difference of 2 squares. Multiplies to -3 and adds to give us 2. Multiplies to -3 and adds to give +1. So my least common denominator is going to be x plus 3, x minus 3, x plus 1, and x minus 1. And each of those occur just at most one time in any individual fraction, so they're all to the first. So far, so good? If I look at the first fraction, I'm missing the x plus 1 and the x minus. I'm missing the x minus 3 and the x plus 1. Oops, that was a subtraction symbol I just miscopied. And then if I look at the last one, I'm missing the x plus 3 and the x minus 1. So now I need to multiply this stuff all out. So that's going to give me 2x squared plus, minus 2. And then that's going to give me negative x cubed minus, plus 2x squared plus 3x. And then the last piece is going to be plus 2x cubed plus 4x squared. So this is just foiled everything out. I made sure I distributed my negative when appropriate, and I did all the distributing and everything. I just did it all in kind of one step. Again, if you need to write down more, definitely okay, right? I'm just trying not to spend, like skimming through that seems like we should be able to handle, right? We're just foiling and distributing and stuff. Okay, so if I combine my like terms, I have a negative x cubed and I have 3 distinct primes, right? I have x minus 3, I have x minus 1, and I have the, right? So each one of those 4 I look at how many times they occur in each individual fraction, and I take the, but they all occur just one time at most per fraction, so they're just to the first. So that's all there is to it. Is that okay? As opposed to something like if you had like this, where your least common denominator, most number of times the 2 occurs is twice. Yes, sir. That's an x plus 1. Mackenzie. On this sheet? Okay. Edmund, you good? Yeah. Okay. Yeah, no problem. Mackenzie, you wanted to do 3. Okay. So x cubed plus 1 is a sum of two cubes. And then x squared minus 1 is a difference of two squares. And then there's division going on here. I'm going to flip and factor at the same time. But the numerator only has a greatest common factor of 3. I notice that there's not two numbers that multiply to give us 1 and add to give -1, so that one is factored as far as it can go. Part, though, we need to find the two things that multiply to give us -15 and add to give us +2. That being 5 and -3. Plus 5x plus -3x minus 5. Out my x. 1, 3x plus 5. So 3x plus, and then x minus 1. And then this piece also is going to get flipped. So the 9x is a difference of 2 squared. Take a greatest common factor of 2x squared out. And now it's just reducing time. And I think that's it. Yes, of course. So we'd say our answer then is 3x plus 5. And I'm going to write it with the squared. You could write it twice if you wanted to. Over 6x squared. And our restrictions are +1 from that piece. This one, the solutions are only imaginary, so we don't have to list them. And then +5/3 from that piece. Yes. Yeah. If they're imaginary, you don't need to include them, but if it's a real number, we do need to. Good. You guys ready to move on here? Do some new stuff? A little bit anyways. Okay. Boy, I felt like I better even touch that. All right. So let's look at a couple of examples. So the first kind of example I'm going to start with is something like this. This is something you guys should have recognized from geometry last year. What is this kind of thing called? It's a proportion. That's where we have one fraction equal to one other fraction. Do you guys remember the strategy that you use to solve a proportion? Yeah, this is where we cross multiply, right? Cross multiplication is not fractions, it's how we solve a proportion. So x is 5x, and then 2 times 3 is 6, so this just turns into the equation equal to 6. All right, so let's look at how this would differ if we were using if this was involving rational expressions instead of just fractions. So still a proportion, right? We have just one fraction equal to 1. So we can still just do the same thing. We can so far so good. Now to solve, multiply everything out. And then we're going to move everything onto one side. And then this is factorable. So we can solve this by factoring. If you didn't end up with a quadratic that was factorable there, what would you have to do? Anybody? You'd use the quadratic formula, right? If you can't factor a quadratic, you can still solve it. Just use the quadratic formula. Are you always going to get a quadratic there? No. It would be better. Sometimes you could get a linear equation, right, where the x squareds just cancel out. That's pretty rad. Could it be worse? Sure. Could be a bigger polynomial. You might get something that's, cubic or quartic or something. Hopefully it's something that can factor. You should be something that you can factor using your factoring tree stuff, though, where you don't have to chapter. That shouldn't have to happen. You should be able to factor it using sneaky factoring tree stuff without having to go and look at the graph and do synthetic division, all that mumbo jumbo. Okay? Now there's one other thing here that we need to make sure that we're doing on these problems, because not every one of these solutions is an actual solution. So when we're solving a rational equation like this, we can get extraneous solutions. Remember that happening in first semester when we solved absolute value equations? Right, where we got an answer that looks like an answer, but when we plug it back in, it doesn't actually satisfy the equation. That kind of thing can happen here still. The check, though, is much easier than it was in first semester. So I don't actually need to make sure that the two sides are equal. Really, all I need to check is to make sure my answer doesn't give me a zero denominator. That's all I really need to check. So if I go back to the very beginning here of this problem, if I plug 1 in, that doesn't make that 0, and it doesn't make this 0, so I'm done, right? That's an answer, I'm good. If I does make a 0 denominator, I discard that solution. The remaining solutions then would be my answer, and if there's nothing remaining, then I have no solution. Everybody okay with that? So it doesn't happen very often, but you do need to make sure that you're aware of it and you are checking. It's pretty rare. It's hard for me to cook up a problem where that happens because it takes a little bit of doing to make sure that works out. Takes 5 minutes for me to come up with a problem that it'll work for it. And it's not easy to do. Requires a little bit of guessing and checking, and so you won't see them very often because it's really hard for somebody to come up with them. But you do need to know that that can happen and they're out there. But overall, a pretty easy to execute strategy, right? A second type of problem, your algebra or pre-algebra classes, would have been something that looks like this. Right? Definitely not a proportion, because on the one side you have 2 fractions of 1. Right? So let's talk about the types of strategies that we could have done. So the obvious thing would just be to add the fractions to make a proportion and then solve that way. Another way, make a least common denominator that's the same on both sides of the equation. And then you can just take the numerators from the right-hand side and set them equal to the hand side and solve that. Third way to talk about is called clearing fractions. And that's where we multiply both sides by the least common denominator, and then we solve what's remaining. This is the one that I'm going to use. Now, all of these strategies are valid, and there's probably some more things that I didn't think of that you could do to solve something like this that wouldn't be incorrect. For the clearing fractions method, well, let's think about this for a moment. If you had your choice between multiplying fractions or adding and subtracting to do, which requires less kind of tedium. The multiplying, right? That's much easier. All you have to do is factor and cross stuff out and you're done. You guys agree? That's the advantage of clearing fractions, to ever have to add any fractions. And that's one of them is to scale really nicely, where the problem gets easier after you've done that. It never gets harder, which is a good thing. But they're all these methods are valid when I'm demonstrating things, because I don't think it's necessary to talk about all 3 of them and make it get confusing as the strategies start blurring together and overlapping and getting confusing. I'm going to do exclusively that. You're welcome to not. Like, you guys can do different strategies if you want. You don't have to, though. I think that the clearing fractions is the best one. Will never be harder than one of the other strategies. So identifying what the least denominator is for all the fractions present, that's just going to be 2 times 3 times 5, right? So I'm going to multiply both sides of my equation by, and show you how. I won't always write out all the work so you can kind of see what's happening. Everybody good? Yeah? We're so good? Okay. Times 5 times 2 is 20. And 2 times 3 times 7 is 42. And we're left with now just something that's really quite easy to handle, right? Divide by 15. Bless you. Rational expressions instead of fractions. Okay? So that's what I'm going to multiply to both sides, rather than trying to squeeze in that whole string of inequality or string of parentheses there, since I've identified what the LCD is below. Okay, we're good. The x minus 2 and the x plus 2's cancel. In the second multiplication problem, cancel. In the third multiplication, x from both sides, and I subtracted 6 from both sides to get to where I'm at. Now that quadratic equation is not factorable, right? So what am I going to have to do then? I'm going to have